Welcome back, everyone. We're diving into a fascinating paper today, all about RR Lyrae stars.
Oh, these are cool.
Yeah, they're like these old pulsating stars acting as cosmic yardsticks.
Mm-hmm.
I've got excerpts from the paper here, and some background you sent over. Should be a fun one to unpack.
Looking forward to it.
So, these RR Lyrae stars, we find them in these, like, really old parts of the universe, right?
Yeah, like globular clusters.
Globular clusters,
Exactly.
and dwarf galaxies.
Dwarf galaxies, yeah. Places where, like, the younger, brighter stars, you don't really see them there.
Right, not so much.
And the really cool thing is, they're what astronomers call standard candles.
Yeah, that's key. Their brightness, it lets us measure distances across, well, huge distances in space.
It's like mind-boggling distances, right?
Absolutely. They're vital for that cosmic distance ladder.
Mm-hmm.
Helps us figure out, like, the scale and structure of the whole universe.
It's like having mile markers, but, spread out across the cosmos.
That's a great analogy. Now, this paper, it uses this infrared surface brightness method
Mm-hmm.
to figure out distances and sizes of these RR Lyrae stars. And they use data from the Gaia mission, that incredible star mapping project, along with observations from telescopes down in Chile.
Combining those gives a really powerful data set.
It does. And the goal here was to figure out this thing called the P factor, which seems pretty important.
Oh, it's crucial, especially for these RR Lyrae stars.
Okay, so I know these stars pulsate, right?
Mhm.
Getting brighter and dimmer. And astronomers use that to figure out distances. But where does this P factor come into play?
Okay, imagine you're watching a merry-go-round, right?
Okay.
Those horses, they're going up and down as they go around.
Yeah, up and down.
Now, if you're only watching that up and down motion,
Mm-hmm.
you might underestimate how fast the whole merry-go-round is actually spinning.
Ah, because you're missing the circular motion.
Exactly. You need to account for that whole circular part of the movement.
So with RR Lyrae stars, we're only seeing part of their pulsation movement from Earth, and the P factor helps us correct for that.
Exactly. It makes our distance measurements more accurate, like adjusting our cosmic ruler, to get the most precise readings.
Ah, that makes sense. So that's what this paper is all about, pinning down that P factor.
Yeah, that's the core of it. And they used, well, a whole bunch of different relationships between a star's surface brightness and its color. Astronomers call these surface brightness color relations.
SBCRs, for sure.
Correctly, SBCRs.
But weren't those relations developed for other types of stars? How they applied them to RR Lyrae stars?
Good question. They essentially tested out different SBCRs, ones that were originally figured out for other stars.
Like what kinds of stars?
Like dwarfs and even Cepheids, those are another type of pulsating star.
So it's like using a map made for one city to try and navigate a different one.
That's a good way to put it. You hope the general principles still work, but you gotta test it out to be sure.
Makes sense. So they had to see if these SBCRs actually held up in the world of RR Lyrae stars.
Right, and for that they needed a lot of data.
I bet.
So they use high-resolution spectroscopy to measure the star's radial velocities, how fast they're moving towards or away from us.
Okay. And I'm guessing they also measured the star's brightness in both visible and infrared light using those telescopes in Chile.
Spot on, they did both. Big undertaking, combining all that data. It involved, like, carefully aligning those radial velocity measurements with the light curves, basically making sure everything's synchronized.
I bet there's a lot of fine-tuning in that process.
Oh, absolutely. Plus, they had to fit mathematical curves to the data, smooth out any irregularities.
Sounds painstaking.
It is, but it's worth it.
So after all that, were they able to actually determine the P factor for these RR Lyrae stars?
They were, and the results are pretty interesting. Depending on which SBCR they used, they found P factor values ranging from about 1.39 to 1.45.
A range of values, not just one definitive answer. Does that make a big difference? I mean, in the grand scheme of things,
Yeah.
for understanding RR Lyrae stars and the distances to them.
Oh, definitely. It does. Even small changes in the P factor, they can really impact those distance calculations, especially when we're talking about objects, millions, even billions of light years away.
Yeah, that's true.
Imagine, like, trying to measure a football field, but your ruler, it might be off by a tiny bit. That
Yeah.
tiny error, well, it can lead to a big difference in your final measurement.
Makes sense. So this range, it basically shows us the uncertainty we still have in our measurements.
Exactly. It highlights what we still need to figure out. And it gets even more interesting when we compare it to what other studies have found.
Oh, how so?
Well, this study, they found P factors that were actually higher than what a previous study found. one that used a different method, something called the SPAPS tool.
And what P factor did they get?
Their values were closer to like 1.24.
So different methods, different results. What does that tell us?
It really emphasizes how the method you choose can influence the P factor you end up with. It's a good reminder that even in astronomy, there's interpretation involved.
Yeah.
The tools we use, they can shape our understanding, even if it's subtle.
It's like our cosmic ruler. Maybe it has different markings depending on how we're looking at it.
That's a great way to think about it. And recognizing those nuances, that's super important as we try to get even more accurate measurements of the universe.
Makes sense. So this paper, it wasn't just about figuring out the P factor. They also looked at the sizes of these RR Lyrae stars, right? Measured their mean radii.
They did, yep. Found that those mean radii range from about 4.04 to 6.41 times the radius of our sun.
Wow, that's a pretty big range in size. Is that what we'd expect based on what we know about these stars?
That's the cool part. Those observed radii, they actually line up pretty well with what theoretical models predict for RR Lyrae stars.
Oh, that's good. Always nice when observations and theory match up.
It is. It gives us more confidence in our models and helps us improve them even more.
Now, no measurement is perfect, right? Yeah. What kinds of uncertainties were there in their measurements?
Oh, of course. You're right. Every measurement has limitations. Here, the uncertainties came from a few things, like how precise their photometry was, the parallax measurements from Gaia, and even just the fact that these stars are variable. They're always changing.
So lots of factors contributing to those error bars.
Exactly. It's a whole mix of things. But being aware of those uncertainties, that's key to good science. Being transparent about the limitations and always looking for ways to get better.
Okay, so we've covered P factors, surface brightness relations, even talked about the size of these stars. But let's step back for a second. Why should someone who's not an astronomer care about all this? What makes these findings significant?
Well, understanding RR Lyrae stars, it helps us understand the universe's scale and its history. These stars, they're crucial for that cosmic distance ladder for figuring out how far away galaxies and galaxy clusters are.
So they're not just interesting on their own, they're tools for understanding the bigger picture.
Exactly. By getting better measurements of these stars and understanding things like the P factor better, we can map the universe more accurately. Trace how galaxies have evolved, even study things like dark energy.
Wow, it's amazing. These stars, they hold clues to some of the biggest mysteries out there.
They really do. Shows how everything's connected, from the tiniest particles to these huge structures in space.
Okay, I think we've covered a lot. Can you sum up the key takeaways for us?
Sure. So we've learned that the infrared surface brightness technique, it's a good way to measure the distances and sizes of RR Lyrae stars, but we've got to remember, the method we choose can affect the P factor we calculate. And even small changes in that P factor can change our distance calculations a lot.
Right. But even with those uncertainties, it's encouraging that the sizes they measured for these stars match what we'd expect from our models.
Definitely. That helps confirm our understanding of how these stars work.
And we've seen how these findings, they don't just tell us about these stars. They help us understand the whole universe, its size, and how it's changed over time.
Yep.
Before we wrap up, I have one last question, something to think about. Since the P factor seems to change based on the method used, how can we improve our understanding of these stars even more and get even more accurate distance measurements in the universe?
That is the question, isn't it? It's what astronomers are actively working on. It's all about exploring and refining our knowledge. And every answer we find leads to even more questions, which is exciting.
Yeah, it's really remarkable how much we can learn from these old pulsating stars and how these tiny variations in our measurements, they can really have a huge impact on what we know about the universe.
It's true. Shows how important it is to be precise, and to keep refining our methods.
Definitely. Well, thank you so much for walking us through all this deep dive into RR Lyrae stars. It's been great exploring these cosmic yardsticks with you.
It's been my pleasure. Always fun to talk about these things.
Yeah, for sure. And to everyone listening, thanks for joining us for another deep dive. We'll see you next time.